Let's look at this conceptual example. It says that a candle is burning in a well-insulated room, taking the room, which includes the air plus the candle, as your system. Determine A. If there is any heat transfer during this burning process that is taking place. The system includes the air and the candle. The system is highlighted by the dashed line. Can you comment on if there is any heat transfer taking place during this burning process?
No,
What
sir.
did I mention about the heat transfer work? They are boundary phenomena. They are taking place between the surrounding and the system. Is the heat transfer taking place through the boundary? Is there any heat coming into the system outside the boundary? Is there any heat going out of the system from the boundary? So essentially, there is no heat transfer taking place within the system. Clear? Now, this is the conceptual understanding. How do you define heat transfer? Heat transfer takes place through the boundary. Then it says if there is any change in the internal energy of the system, what are the four forms of internal energy? Burning is which form of internal energy? There is
Chemical.
chemical energy that is being, yes, agreed. There is chemical energy that is being generated and it is converting into this burning process. What is it doing? It is giving energy to the molecules of the air. That means the molecules of the air would have higher kinetic energy. This form of energy, molecules having higher kinetic energy, is which part of the internal energy? Is the sensible part of internal energy. So what is essentially happening is one form of internal energy is transforming into another form. That is, chemical energy is transforming into the sensible part of internal energy. But actually, there is no heat transfer increase in internal energy that is taking place. Why? You identify the loss. What is the loss? Either you identify the loss. What is the loss in energy? I am asking you, what is the loss? Tell me the loss. So heat is going where? So there is no loss taking place. Only one form of internal energy is transforming into another form. Clear enough? All right. Moving on, you have another example. The explanation is also given alongside. So you can read it at your own time. This is an example which says that a potato which is initially at room temperature is being baked in an oven that is maintained at 200 degrees as shown below. I'll show you the image. Is there any heat transfer taking place during this baking process? So you have a potato which is placed within the oven. Is there any heat transfer taking place in the system? All right, those in the online mode, is there any heat transfer taking place?
Yes, sir.
How?
From air to potato.
Sorry?
सर सिस्टम अगर पोटैटो सिस्टम है तो फिर एयर से पोटैटो.
So he says if the potato is the system, then there is heat transfer. So that means that it is an open-ended question. You have to define your system first before you could define whether there is any heat transfer taking place or not. If the potato is your system, then yes, there is a heat transfer taking place from the oven through the boundary of the potato to the inside of the potato. Clear? But if your oven is your system, then essentially there is no heat transfer that is taking place. Clear enough? All right. This is not the last question. This is the question whether there is a heat transfer taking place. You have to define your system first before you could say or comment something.
Excuse me, sir.
So you have GG.
सर देयर इज अ क्वेश्चन सर. अगर हमारा ओवन जो है वो सिस्टम है तो फिर भी तो हम एनर्जी ट्रांसफर तो हो रहा है ना. मतलब कि बाहर से एनर्जी तो आ रही है ओवन के अंदर. मतलब इलेक्ट्रिकल एनर्जी जो है वो तो सिस्टम का हिस्सा ना हुआ ना.
No,
तो वो तो
that if you, I'll tell you, I'll tell you. That means the heaters of the oven. If you are considering oven as your system and you say that heaters are part of your oven, so that means heaters are included within your system. If yes, you say that the
Yes.
heaters are not part of the system, then the energy would transfer from the heaters to the solid body, which you call it as oven. Clear?
नहीं सर, तो फिर हीटर्स के पास हीट कहाँ से आई? मतलब हीटर, लेट्स से हीटर सिस्टम का हिस्सा है, और तो हीटर्स के पास हीट कहाँ से आई? मतलब एनर्जी कहाँ से आई?
हीटर्स के पास हीट
एनर्जी,
आई, इलेक्ट्रिकल एनर्जी विच इज
जी
electrical
सर,
energy which is work, electrical
यस
energy which is defined as work. All right,
जी सर.
heat transfer is only referred to when there is a temperature difference. If there is transfer due to temperature difference, that is when you say that heat is being transferred. All right,
यस सर, राइट.
clear?
यस सर, इट्स क्लियर. थैंक यू.
जी, तो बढ़ता जाए, कौन सा ट्रांसफर हो गया? When you are talking about the system, if it is an insulated system and the energy is generated within the system, is there any heat transfer taking place or not? Simple question. No. But if you take potato as your system, yes, then there is heat transfer taking place across the boundary. It depends how you define your system. Moving on, the electrical work. Yes, your question. What you were referring to was the energy. Where did the energy was coming from? The energy was coming from electrical work. That is the work due to the potential difference V and the charge that was moving across that potential difference. So electrical work is defined as the potential difference multiplied by the charge that is flowing through that potential difference. And if you have to express in terms of power, the power, electrical power, is defined as rate of change of a rate at which this charge moves, which is essentially current, multiplied by the voltage. So the electrical power is defined as voltage multiplied by current, which is expressed in terms of watt. And if you see there is a dot on top of it, that means this work is expressed per unit time. In case your voltage and, all right, you already know that as per the Ohm's law, V is equal to IR. So this power can also be equivalently expressed in terms of I square R or V square divided by R. In case your voltage and current are changing with regards to time, then if you have to calculate the work done, you would have to integrate voltage and current with respect to time to calculate the work done due to electrical work. All right. In case they are constant, the amount of work done is basically VI multiplied by the time that you are referring to. Clear enough? Moving on, the mechanical forms of work. Now we'll be looking into different forms of mechanical work that fall into the category of work. There are two requirements for mechanical work to take place. One is that there should be a force acting on the boundary, and number two, the boundary must move. So the simplest example is that of force into displacement. That means if you have a wooden box over here and you apply a force at the boundary of that wooden box such that the box moves through the distance S, you have essentially work done equal to force into displacement. Clear? If the force is not constant and there is a relationship with the distance it is moved, you will have to integrate in order to get the work done, so that you have a relationship between force and displacement. And in case you are sleeping, you're not moving, the work done is essentially zero. Clear? The shaft work is basically associated with the torque. If you have a force, if this is my arm and apply a certain force onto this arm in this way, with regards to this elbow as my pivot, so there is a force acting downwards that is creating a torque. And what is this torque? It is equivalent to the force multiplied by the moment arm. All right. And if I have to express force in terms of torque and the moment arm, it is basically torque divided by the radius through which it is acting. Clear? All right. Now, if I have to convert, all right, this torque, when I'm applying it onto a shaft, basically, this is the force acting, and as a result, the shaft moves. What is the distance that shaft moves as a result of this force? What is the distance a shaft is moving as a result of this force? It is basically the circumference, 2 pi r, the circumference it is moving. If it makes one revolution, it is 2 pi r. If it makes multiple revolutions, it is 2 pi r multiplied by the revolutions. So the force multiplied by the distance the system has moved due to that force is basically, this is the distance which the shaft has moved due to the application of this force, and the work done would be again force into distance, where torque over r is basically the force and 2 pi rn is the distance the system has moved due to this force that has been applied onto it. Clear enough? Now if I want to convert this work done into power, work done is converted into power by dividing it with the time. So if I express the revolutions in terms of revolutions per minute, it would essentially be converting the work done into power. So if I multiply, instead of multiplying it with 2 pi torque into number of revolutions, if I multiply it by n dot, which is revolutions per second, I would essentially be getting the power generated due to this force. Clear? The pictorial representation is also given. If this force is applied to this shaft or system for the distance r, the distance it moves is basically 2 pi r, or 2 pi r multiplied by the times it moves, that is the number of revolutions. If I express the number of revolutions in per unit second, it would be basically converting the work done into power. Clear enough? Moving on, the spring work. So we are looking into different forms of mechanical work. If a force is applied onto this system boundary over here, if there's a force is being applied, and as a result of this force, the system moves by a displacement of dx, the work done would essentially be what? The differential work done, if you see, it is written in inexact form. Since it's not a state function, it is a process, or it is dependent upon path, this is basically expressed as inexact differential. So the work done, differential work done, would be force multiplied by the distance it has moved. In order to calculate the total work done, I have to integrate it, and for that I need to have a relationship between force and displacement. All right, when I have to integrate on both sides, on one side I'll have the total work, on the other side, if I have to integrate, I need to have a relationship between displacement. And the Hooke's law gives you a relationship for the is that force is basically to do. If I plug it into this equation, I would be able to integrate and for the force, the displacement would automatically be double. Work done due to spring that I'll get. That means if I plug in, instead of F, I plug in Kx and I integrate with respect to dx. Kx dx, I integrate it from 1 to 2. I would have Kx square with the limits 0 to 1 or 1 to 2. Clear? Is this point clear? G. Convention you can use, but the generic form would be the same. When you integrate, it would automatically be incorporated. Clear? देखें जी ऐसे ही था हाई स्कूल फिजिक्स है. Is it clear? Work done to accelerate a body or work done to raise the elevation of a body is essentially also work done, or a mechanical type of work done. That means if you provide energy to a body such that it accelerates with a velocity, it is basically doing some mechanical work on the body. So kinetic energy is essentially a part of mechanical work. Similarly, if I have a bottle over here, I raise it to a certain height. By doing some work on it, I am basically increasing the potential energy of the body. So potential energy and kinetic energies are the recognized form of mechanical work. Clear? This is the example where motor is basically pulling the elevator. So motor is doing work which is resulting in increase in the potential energy of the system, which is your elevator. Clear? There are other non-essential or non-mechanical forms of work. You don't need to have a very good understanding of it because they are not included in the thermodynamic systems that you study. One of that work you have already studied is the electrical work, which is basically voltage multiplied by the charge, or if you are expressing in terms of power, it is voltage multiplied by the current. Clear? Then there are other works, which is magnetic and electric work or electric polarization work. That is, uh, in this kind of work, force is synonymous to the strength of the field. That means the normal force that you see in other mechanical applications, in these magnetic or electrical work, it is the field strength which replaces force. Field strength is the force acting on a unit charge. All right. And the polarization is basically the displacement. All right. Polarization of charges is the displacement, and the electric field strength is basically the force. Clear enough? Moving on, we have two examples to look into. We'll quickly look into these two examples. One is that you have to determine the power required to accelerate a body of 900 kg from 0 to 80 kilometers per hour in 20 seconds. So what is the power required? Now, this is the mechanical form of work. You are accelerating your system, which is your car, from 0 to 80 kilometers per hour, and your system has an overall weight of 800 kg, 900 kgs. Can you calculate the power required? You have to do this in 20 seconds, this process in 20 seconds, not the calculations. So what is the power required? How would you do that?
Sir, kinetic energy divided by the time.
So kinetic energy divided by the time. The only
Yes.
thing critical over here is the units. Yes, please.
No, sir, I was just saying the same.
Yes. The only thing critical over here is the units. Whenever you are expressing energy, be mindful. Kilometers is not the right unit. Hours is not the right unit. All right. So you have to express in terms of meters per second before you could answer in the units of energy, which is joules normally. All right. So the only critical thing over here is that the problem is basic physics problem, that you have to apply the energy equation, which says that work done is equal to change in, or is equal to the change in kinetic energy. And the only critical thing is that you express the velocity in meters per second. And once you have the velocity, you divide by the time duration given to you, it would give you the power required. Clear enough? Then you have another example where it says that a car is a car which is having a mass of 1200 kg is cruising steadily on a level road or a horizontal road at 90 kilometers per hour. Now the car starts climbing the hill, which is sloped at 30 degrees. If the velocity of the car is to remain constant, determine the additional power that must be delivered by the engine. क्या करोगे?
सर
जी बताइए.
सर कंपोनेंट्स की जरूरत हाइट के लिए, हाइट फाइंड करने के लिए कि हाइट 20 सेकंड्स का ही टाइम है ना, कि उस टाइम में हाइट कितनी अटेन कर ली है
20 seconds? There is no mention of 20 seconds.
No, is it not the same part of the previous
No,
one?
it's not the part of same problem. It's a different problem.
Okay, sorry.
What is the additional power required for?
Sir, for the increase in the potential energy.
For the increase in the potential energy. So,
Yeah.
if the road is horizontal, your car is moving at 90 kilometers per hour. In order to move at an inclination of 30 degrees, there is an additional power required to cover the elevation. All right. So essentially, the energy required is the energy to gain potential energy, and the components for potential energy are what? mgh. Mass is constant, gravity is constant, height is changing, and if you see, the required answer is not in terms of energy, it is in terms of power. That means height divided by the time. Clear enough?
Yes. Yes.
So if you look carefully, basically the only thing that you are required is to find out the vertical velocity. That means change in height with regards to time. For instance, delta z over delta t. If I, for the moment, for just few minutes, if I ignore delta t at the moment, mg delta z, which is this value, is basically the potential energy. And if I divide this potential energy with the time, I would have basically the vertical velocity. And this would convert, the work would convert into power. Clear? So the only thing needed is basically the vertical component of this velocity, which would give you the additional power required. Clear enough? And be mindful, again, you have to use this conversion to have the units in joules, and this conversion to convert joules into kilojoules. Clear? So essentially you would have 147 kilowatts. Clear enough? So I'll stop over here because you are